speaker today is Stefan Mendez Diez, who is from the University of Alberta and whose birthday it is today. So he wrote about K-theoretic and string theory.
Okay, so this is joint work that I did with Jonathan Rosenberg, and the paper we found on the archive. So what we're going to be looking at is a hypothesized duality between the type 1 theory on a 4 torus and the type 2a theory magnified on a 3 surface. It's actually a pretty interesting duality. It's possible to relate all 5 superstring theories through this duality. So going from the type 1 to the type 2a theory, you actually factor through the SO32 heterotic theory, where the type 1 on T4 is dual to the SO32 heterotic theory on T4 via an S duality, and then you do a string-string duality, you get to the type 2a theory on K3. Then if you look at the orbifold point of the moduli space of K3, which is T4 mod T2, where the T2 action is multiplication by -1, that is T-dual to the type 2b theory on that orbifold, where you then have an NS5 ring at each of the 16 double fixed points. And then you can do another S duality, where all the NS5 branes will transform to B branes, and you're back at the type 1 theory on T4. So we're going to look at some of the K-theory classifications of RR charges in the 2 theories. So we say that 2 theories are dual to one another, they should have the same spectra, and so it should be possible to match the groups that classify the RR charges in the 2 theories. It's important to note that, we're mainly going to be looking at D-brane charges, and under a duality, a D-brane might not actually transform into another D-brane, but there should be some other object in the theory that you can equate with the D-brane in the dual theory and should have the same charge. You should still be able to match charges. So, for classifying D-brane charges in the type 1 theory, we want to use KO theory, real K theory. And since we need everything to be 10-dimensional, we want to look at Q4 cross R6. And we find that KO of T4 cross R6 is 6 copies of Z and 5 copies of Z mod 2. So if we, for the type 2A theory, we want to classify the charges by K1 of K3, and that's 0. I guess I should say that K0 of K3, which would classify charges in the type 2B theory, is 24 copies of Z. So we sort of see in an immediate problem that these groups do not match, and it would seem to imply that we have no RR charges in the type 2A theory. And so we're mainly going to be focusing on the torsion charges. Still need to do some work to figure out the non-torsion charges. We'll get an exact matching on the torsion charges. And I just want to really stress that the only gauge fields in the type 2A theory on K3 come from the RR sector. So the only charged objects are D-branes. The only way to really describe these torsion charged D-branes that occur in the type 1 theory would be by torsion charged D-branes in the type 2A theory. I will also point out that if we want to classify the charges on the orbifold, we need to use equivariant K-theory, and I'll talk about that a little later. So in the physics literature, often use a blow-up of the orbifold limit of K3 when dealing with K3. And so there's 16 isolated double singular points, and so this is usually blown up by excising the singular points, and then you have 16 boundary components that are all RP3, and 16 copies of the Gucci-Hansen space, which is the unit disk bundle of the tangent bundle of the 2-sphere, are usually glued back in along the common boundary, which gives you a manifold, smooth manifold with the same topology as K3. And we know we don't want to do this because since we have the same topology as K3, we have the same K-theory, and again, we would see no RR charges on the type 2A side. So what we decided to do instead is to look at a manifold we call N, where we just left the singular point size. So what we did is we just took 16 open balls out of T4 and then did the Z2 action to get a smooth manifold with boundary of 16 copies. There are 16 copies of RP3. Now we don't, since we were sort of originally considering the type 2A theory on a smooth K3 surface, we don't want to allow for any physical effects from the orbifold points. As orbifold points are sources for RR charges, just like D-branes. So what we want to look at is the orbifold mod the singularity, sort of mod out the effects in the singularities. And so this is the same as taking our smooth manifold N and modding out the boundary. So, to classify D-brane charges in N mod the boundary, we want to look at the K-theory of N relative to this boundary. So to do that, we first need to compute its homology, which we do with the following spectral sequence, where the E2 term is the homology of Z mod 2 with coefficients in the homology of M, where what I'm calling M is the double cover of N. So it's just the 4 torus minus the 16 open balls. Then we can use the Hertzebruch spectral sequence to compute the K-theory. We actually get an extension problem, but that can be solved using Mayer-Via torus, where we use N 16 Figuchi Hansen spaces in K3. So we find that K1 of N relative boundary is 15 copies of Z and 5 copies of Z mod 2. So we've got that match on the torsion charges that have some extra integral charges. Now, for the type 2B theory, we want to do something a little bit different because the 2B theory is T-dual to the type 2A theory at the orbital point of the moduli space. So there's actually, we need to sort of take into consideration what's happening at the orbital point. There, as I said, there were NS5 branes located at each of the orbital points in the 2B theory. So what we're going to do is move those branes away from the orbital point and sort of consider them located at the boundary of N. So rather than modding out by the boundary of N, we actually want to look at the absolute K-theory of N. And so we can get that from the relative K-theory that we computed just using a Poincare duality, and we get 7 copies of Z, and again 5 copies of Z mod 2. So we've gotten an isomorphism on the torsion on all 3 groups that we looked at, the KO of T4 across R6, K0 of N, and K1 of N relative boundary. So that was a pretty good thing that we're able to recreate the torsion charges, but we still have these extra Z summons coming up in the last 2 groups. And so we have sort of 2 ideas of how we can maybe describe these extra charges. One is that it's known that there are non-supersymmetric branes in the type 1 theory on T4 that could possibly map to supersymmetric branes in the type 2A theory. Well, it's known that some of these branes exist. It's not really known which ones actually transform to supersymmetric branes. But
whether a brane is supersymmetric depends on which theory you're describing it in. I don't understand.
But before talking about that, are you sure that the D-branes in original description becomes again D-branes?
Well, actually,
They don't necessarily.
We know they don't.
Then why do you compare K-theory and K-theory? Because K-theory only classifies D-branes, not...
Right, but on the 2A side, the gauge fields are only coming in from the RR sector. So the only charged BPS objects are D-branes.
There are wrapped NS5 brains, for instance. There's the fundamental string. Those are VPS objects.
The fundamental string on the 2A side is uncharged. And I mean, when you
uncharged under the Ramon sector, but it's charged under the NS form. In fact, it's the...
But it's uncharged under 6-dimensional gauge fields, I think is what he's trying to say. So in 2A, you've only got odd Ramon forms.
It's a string.
It's a string.
It is charged under a gauge field, 6 dimensions, so the field can't physically.
Well, okay, sorry, I mean vector.
And when you map it, when you look at it in the heterotic theory, right, the fundamental string in the type 2A side is going to appear as an uncharged soliton in the heterotic theory. Whereas the charged D brains will appear as charged solitons.
So that's 5 brains. It has to be on the right side of the duality. The 2A fundamental string is on the right side of the duality.
Yeah, but it's appearing as an uncharged soliton in the heterotic side.
I mean, the 2A 5 brain, so the 2A fundamental string in 6 dimensions is the D5 brain of type 1 wrapped on the T4. Right? So that was something that was charged on the Ramon. On the type 1 side is something that's has net Nibber-Schwartz charge on the type 2A side, and vice versa.
But there are other.
I mean, there are lots of other things, but I mean, there you already see that things that were Nibber-Schwartz carried Nibber-Schwartz charge on one side of the duality, carry Ramon charge on the other side, and vice versa. So even before you get to the torsion charges, right, the free part of the charge lattice, right, mix it, Nibber-Schwartz, and Ramon get mixed, get exchanged. Right? Even before you get to the torsion. Right? Just rationally they get exchanged.
Well, when you go to the sort of between the type 1 and the 2D side, you're interchanging the Nibber-Schwartz brains and the D brains. But on the 2A side, you're going to have the only way to really account for these charges.
No, I'm talking about the 2A.
I guess I'm taking this from a few references that I've referenced in my paper, and maybe we could talk about afterwards, where they claim that the only BPS charged objects occurring on the 2A side should be these charged D brains. So another thing that happens at the orbital point of the moduli, there are D2 brains that graph 2 cycles located that shrink to 0 size at the singularity. And these 2 cycles, while they shrink to 0 size, the brain's tension remains finite. But under certain conditions, these pairs of BPS D2 brains can decay into single, stable, non-BPS brains. So these D2 brains sort of correspond to the blow-up modes of the orbital singularities, and they map under the T-duality of the type 2B theory to D strings that stretch between the NS5 brains located at the singularity. So the moduli, the blow-up modes map to moduli that control the position of these NS5 brains. So when we move these NS5 brains, we've changed the mass of these D strings and ultimately changed the mass of these D2 brains via the duality, and depending on which mass is larger, the sort of pairs of BPS brains or the single non-BPS brains will depend on which one is a stable configuration. So in the sense that there are, you could sort of describe a single D2 brain as a pair of these BPS brains that could possibly reduce the free rank, because those correspond to integer charged branes. So we sort of combined some features from the orbifold and the smooth K3, and we need to sort of get an idea of where these different charged branes are coming from to sort of figure out what should be included and what shouldn't be included. So sort of a first step to that is to look at the charges on the orbifold itself. So we're just going to do this for a general N torus, just to get some apply to other situations, and we need to use the Z2 equivariant K-theory of an N torus to classify these charges. So what we find is that the equivariant K-theory of an N torus is entirely localized in degree 0. R is the representation ring of Z mod 2, and T is the non-trivial character. So as it let me just sort of say how this is proved. But the idea is that if you use Isler's theorem by Siegel, where you get this exact sequence where C is a closed G invariant subspace of a G space X. So if you remove sort of the N cell from the N torus, you're left with some N-1 tori whose pairwise intersections are N-2 tori, and the N-1 tori are a closed subset under that G action, so you can sort of build up by induction to get this formula. So this gives us sort of the R module structure of the G equivariant K-theory of Tn, and sort of physically this only would be very useful when N is even. When N is odd, the Z2 action reverses orientation, and so we'd also have to include sort of a world sheet orientation reversal, and we probably want to use K-R theory to classify those charges. But for when N is even, which is the case we're looking at, this classifies these R charges. And let that slide out, but I guess we should just want to say that this, as an abelian group, agrees with the K-theory of K3. So, it's good that we actually do get that match. It doesn't matter if we're looking at the equivariant K-theory of T4 or at the just ordinary K-theory of K3. And then finally, we can use that to get the R module structure of the K-theory of N that we were looking at before. So here is M, again, is the double cover of N, so the Z2 equivariant K-theory of M gives us the K-theory of N, that manifold we were looking at. And so this is for the 2A side, what we were looking at before. We get the R module structure there, and for the 2B side, we have this. This is the R module structure, which gives us some sort of added information to consider where these various charges are coming from relative to the fixed points or from the bulk of the smooth K-theory.
Questions for Stefan? Or comments? Or if there's no question, then Frank, again.